reading, pairing every image with a caption, learning the world through words. Others, they just look, no text, no labels, just raw pixels and curiosity. This paper explores what happens when we take self-supervised vision models and scale them up. We're talking 7 billion parameters, trained on 2 billion web images, the same data used for CLIP, but without any language supervision. And the result, surprisingly strong. These vision-only models don't just match CLIP on classic tasks, they close the gap on multimodal benchmarks too, even in text-heavy domains like OCR and chart understanding. So maybe, with the right scale and the right data, seeing really is believing.
There's been a divide in computer vision between models trained with and without language. On one side, you have contrastive language image pre-training, CIIP, which I'll just call CLIP from now on, trained using image-text pairs that pick up on rich semantic cues from language. On the other side, you've got self-supervised learning, or SSL, which learns purely from images, with no text involved at all. Historically, SSL has been very strong on classic vision tasks like classification and segmentation. But for tasks like visual question answering, VQA, which I'll just call VQA, CLIP has usually held the edge. Why? Is it because CLIP uses language, or because it's trained on huge web-scale data? This paper sets out to answer that question. The authors train CLIP and SSL models on the same giant dataset, MetaCLIP, and compare them on 16 different VQA tasks. Check out Figure 1 here. It shows that once visual SSL models scale up in data and model size, they can match or even outperform CLIP. The biggest surprise? They do really well on tasks like optical character recognition, OCR, and chart interpretation, tasks where you'd expect text supervision to matter. So the big takeaway is that language might not be the secret sauce. If you give SSL enough data and a large enough model, it can stand shoulder to shoulder with these multimodal giants. Now let's look at what the authors call Visual SSL 2.0, a major upgrade over previous self-supervised pipelines. They argue that to compare SSL with CLIP fairly, you need to scale up both data and model size and then really put the models to the test. First, there's the data. Older SSL work typically used smaller sets like ImageNet or maybe LVD142M. But here, the models are trained on a web-scraped dataset of more than 1 billion images, referred to as MetaCLIP web data. That's a big deal, because it puts SSL on the same playing field as CLIP in terms of sheer volume. Second, they increase model size dramatically, from 1 billion to 7 billion parameters. That jump lets them see performance trends that stay hidden when you only train smaller SSL models. Finally, there's the evaluation. They don't stop at standard benchmarks, like classification or segmentation. They also test on more demanding tasks, like answering questions about images, logical reasoning, and interpreting embedded text in charts. The latter is where CLIP had been expected to shine. Look at the figure here in this section. It illustrates how they move from small-scale setups, little models, and small datasets, to this big data, big model regime. It's a clear message. If you want SSL to contend with CLIP, you need to think bigger all around. And, based on early hints, SSL scales up beautifully, especially for images that contain text. Next, let's dig into their experimental setup. They're deliberately matching CLIP's training data. Instead of smaller collections like ImageNet, they use the massive MetaCLIP dataset. It has over 2 billion web images. But in the SSL case, the models only see the images, no text. That's how they keep the comparison fair. If the SSL models do well, it's definitely not because they learned anything from language. They also vary model size in a structured way. This is where vision transformers, or VIANT, come in. A VIANT is an architecture that applies the transformer mechanism to image patches. Here, they train 5 different VIT models, ranging from 1 to 7 billion parameters. Each model scales in width, depth, and other internal dimensions, as shown in Table 1, helps them see how capacity alone affects performance. For evaluation, they don't just stick to standard vision metrics. They lean heavily on VQA, which tests broader skills like reasoning, reading text in images, and interpreting charts. To keep things fair, they use the same 2-stage tuning across all models. First, they attach a small projection layer to link the vision encoder to a language model. Then they fine-tune the system, freezing the vision part. The section ends by kicking off their study of scaling. First, they fix the dataset at 2 billion images and grow the model size. Later, they'll flip the script and see what happens if you keep the model size constant but scale up the data. Here, the authors show how model size and dataset size impact SSL performance on VQA. Look at Figure 3. It plots performance against the number of parameters, from 1 to 7 billion. For the SSL approach, they call Web Dino. More on Dino in a moment. Performance rises almost linearly as the model grows. This is true across all VQA tasks, and it's especially noticeable in categories like OCR and Chart and vision-centric questions, which might have seemed to require text supervision. By contrast, CLIP's performance plateaus around 3 billion parameters. So while CLIP starts out strong at smaller sizes, it doesn't keep improving as much at larger scales. They also show category-specific results. On OCR and Chart tasks, WebDino doesn't just catch up, it actually surpasses CLIP at 5 billion parameters and up. Yes, this is an SSL model that's never seen text during training, and yet it's beating a model that was trained on image-text pairs. That seriously challenges the idea that text supervision is a must for OCR tasks. Then they shift to dataset scaling. They train on anywhere from 1 billion to 8 billion images. You'll see the biggest gains in vision-centric and OCR and Chart tasks, which keep improving past 8 billion samples. It's a sign that SSL thrives on large, diverse data, even for tasks that seem text-heavy. Overall, it's a big statement. With enough data and enough parameters, purely visual SSL can rival or even surpass CLIP. In the next figure, Figure 4, you'll see how training data size alone affects the biggest SSL model, the 7 billion parameter WebDino. They try 1 billion, 2 billion, 4 billion, and 8 billion images. And it's pretty straightforward. More training data, higher accuracy. The benefits do taper off for some tasks, like general VQA, after a few billion images. But OCR and Chart performance just keeps climbing. What's eye-catching is that in every category, WebDino eventually beats CLIP if given enough training data, even though CLIP sees images paired with text. It really shakes up the notion that image-text supervision is necessary. Then Section 4 begins by asking 5 big questions about why scaling helps so much. First question: does this scaling trend hold for other SSL methods? They test another method called a masked autoencoder, or MAE, which reconstructs masked portions of the image. MAE also scales nicely with data and model size, especially on OCR tasks, though it has some trade-offs on other benchmarks. They also check how these SSL models do if you only train them on something classic like ImageNet. The result? Not good. Even bigger models barely improve. So it's not just about size, it's about large and diverse web-scale data. Now they compare 2 flavors of SSL, WebDino and WebMAE. Dino stands for self-distillation with no labels, but it's basically a self-distillation technique. MAE, or masked autoencoder, tries to reconstruct missing patches in images. Both scale effectively, but each has different strengths and weaknesses. Look at Figure 5. As model size increases, WebMAE's accuracy rises across the board, particularly in OCR and Chart tasks. In fact, it often outperforms WebDino in that niche. That suggests MAE's reconstruction objective might be especially good at learning text-like patterns in images. Then Figure 6 digs into pre-training data. A model trained on ImageNet 1K doesn't improve much, no matter how large it gets. But with MC2B, a web-scale set, accuracy keeps going up. That holds for both VQA tasks and standard metrics like ImageNet classification. The diversity of web data seems crucial. It contains charts, diagrams, and other real-world visuals that push the model to develop more general features. Why the big jump in OCR performance? The author's hypothesis is that web images naturally contain lots of embedded text. Even without explicit labels, an SSL model can learn those text cues simply by reconstructing or contrasting them during training. This section shows that these huge SSL models also do great on traditional benchmarks. Check out Figure 7. WebDino does really well on classification, segmentation, and even depth estimation. Its performance scales right alongside model size, from 1 billion to 7 billion parameters, and in many cases, it even outperforms MetaCLIP. Without using fancy high-resolution tricks, it's right up there with DyNov 2, so it's clear SSL isn't just for multimodal tasks. Then things get even more interesting when you look at Table 2. The researchers selectively filter the training data to include images that contain text. There's a light filter, 50% of the data, and a heavy filter, 1.3% of the data. The heavily filtered set, though much smaller, gives a massive boost to OCR and chart tasks. It even beats CLIP, VIT2B on some benchmarks like Document Visual Question Answering, DOCVQA, and OCR Bench. The gains are in the double digits, which is huge. This suggests you can sometimes outperform a brute force approach or language supervision simply by curating data to better match your target tasks. Look at Figure 8. You'll see a breakdown of what the raw dataset looks like versus the filtered ones. The filtered sets are loaded with charts, tables, and other text-rich images, which is exactly what the model needs for OCR reasoning. It's a powerful demonstration that it's not all about dataset size. The content of the data matters just as much, maybe even more, for text-specific tasks. Now they address a fascinating question. How can an SSL model that's never seen text embeddings align so well with large language models, LLMs? To test this, they compare embeddings from their vision-only encoders and an LLM on a dataset of Wikipedia images and captions, measuring how close those embeddings are. No fine-tuning, just a raw check of alignment. See Figure 9? It shows that WebDino aligns better with Llama than older methods like Dynov2. Larger WebDino models do better than smaller ones, and those trained on more images, up to 88 billion, do best of all. This implies that just scaling up data and model size allows purely visual models to pick up text-sensitive features, even though they never saw text at pre-training time. They then analyze how their best web SSL models, both Dino-based and MAE-based, perform across VQA and classic vision tasks. Everything so far is at a resolution of 224 times 224 for consistency. But the highlight is that these SSL models can even outperform well-established models like MetaCLIP and SigLip2. And they do it without using any text during pre-training. Finally, the authors hint they'll take things beyond 224 times 224. Higher resolution might bring even more gains. Let's see how that turns out. Here comes the big scoreboard. Check out Table 3. It compares a range of models, some that learned from image-text pairs, others from images alone, across a bunch of tasks. Models like MetaCLIP and SigLIP have traditionally excelled at VQA tasks that involve knowledge or OCR. But watch what happens when you crank up resolution for WebDino VIT7B. At 224 times 224, it's already in the same league. At 384 or 518, it pulls ahead in tasks like ChartQA and DOCVQA, all without language supervision. This table also shows how older SSL approaches, like standard MAE or a smaller Dino, might lag behind if they're not scaled up. They do fine on ImageNet or depth estimation, but bigger tasks like VQA need more capacity and broader data. Overall, this results table is the culmination of all the hints in the earlier figures. SSL, when done at scale with the right data, can go head-to-head with models that use language. Sometimes it even takes the lead. After this comparison, the paper shifts into related work. It situates these findings within the broader context of joint embedding methods and masked image modeling, showing how scaling up merges the strengths of both. Finally, we reach the end of the paper, where the authors discuss limitations, future directions, and how their work fits into the big picture. One notable limitation is that their models aren't designed to do zero-shot text-to-image tasks by default, unlike CLIP, which can. But they mention that you can still plug their vision encoders into a multimodal system, like a tuned LLM, and get impressive results without needing to retrain from scratch. The discussion then drives home the key point. With enough scale, big models, big data, and careful attention to data diversity, purely visual self-supervised learning can produce features as good as or better than those from CLIP. The OCR and chart interpretation tasks are especially eye-opening because they're typically seen as language-heavy. Yet SSL models, fed with diverse web imagery, learn to handle them anyway. The paper closes by highlighting how it bridges two camps in vision: joint embedding approaches and masked modeling approaches. It underscores a broader shift away from relying on text supervision. Given the progress shown here, it might not be necessary anymore. All you need is a giant pile of images and a model big enough to absorb them. And you can do great on both classic vision benchmarks and more demanding tasks like VQA. And that's the story. No explicit language data, just scale and diversity. Plus plus some careful evaluation to unlock powerful visual representations. Thanks for joining us today. Happy exploring!